Good afternoon. Today was the 29th of March, 2023. And what we'll be reading again today is from Chapter 4 of Maugin's Electromechanical Effects and Applications, Nonlinear. And what followed from the last discussion was it kind of concluded with a description of that mathematics is enduring, and really it's the same study classically that it's ever been. And that super classically it's still the same study, and that mathematics is an abstract thing available to any agent of cognition and reason, and that mathematics is a neat rule that we can quite well rely on, and that with regards to a development from a philosophy of dually null and universal, or dually void and whole, or uh, dually infraconsistent, itself in together, itself consistent, that what we're left to arrive at then is that it very well satisfies the desiderata of what makes for our conscientious and conscious approach to the scientific method. That physics then as a science, and as to where mathematics is a logic, and then that the study of mathematics and its knowledge can be a science, that it results that there are many fundamental philosophical approaches what result that after philosophy, after logic, after mathematics, then it's even so natural that the physics as a science arises, and that these are the kinds of things that we attain to. That besides that there is some perfect theory, or that there is a natural world where there is fundamentally a physical law, and these notions of that as we are objective creatures, that anything that so inhabits this universe is as of a thing. Then it's as well that starting from the medium, the milieu, where in the middle of things, that as thinking beings, and objectively and subjectively, and as of each other and each ourselves, that what is then of today's usual dogma, the well-founded and the regular, is that if for something like set theory and the Mengenlehre, and what that means with regards to then the choices that were made, the decisions to arrive at what is the regular and well-founded, then has that it's still attaining to this thing. And then when we reach the bounds and the limits of what are the arithmetizations and the models of these theories, that they are, according to Gödel, incomplete or inconsistent at best, that it's still a so that we're attaining to a more perfect model that is along the lines of something that is consistent and complete. So that was kind of the idea of then that the continuum as a mathematical object is central instead of ultimately derived, that is primary and fundamental instead of that it's utterly eventually evanescent, or unapproachable, or intangible. That it really is the tangible, and it really is the substrate of our continuum analysis, and that the conceit that we have in place about particle wave duality, about the notion of the indeterminism of what's called Heisenberg uncertainty, and a lot of these other things that result from our models being so limited, thus gaining their strength from not going outside their bounds, and where all of our mathematical models are well defined in what they say and can only say what they say. That there's yet the deduction allows us to arrive at that there's this greater milieu, this greater context, that makes so that as a matter of the medium, it's possible to arrive at via reason what would otherwise be unavailable to experiment. That we can develop according to our fundament, and the constancy and variation and diversity and variety of this, as it was put by Gene Roddenberry or somebody, the infinite diversity and infinite combinations, as what so results yet from a linear and a constant and an original analysis, that then the modern foundations have a perceived missing part, with regards to what mathematical formalism of the regular well-founded set theory offers in the eventual description of what's called descriptive set theory in the theories of fields and the theories of after algebra and arithmetic, that the theories of functions as for the operator theory and the operator calculus, then for these different parts of the fields that affect the physics field, which is in essence an abstraction of a place for everything in the universe in this continuous space-time manifold called the universe, including its contents, that there is something to be said as for why mathematics owes physics what are these real mathematics of these non-standard yet real quantities here that the nonlinear theory attains to in terms of potential theory, and it's well understood and according to our theory, and it's already been put in place and left a place for it in the theory, the potential theory, that the people who built the science were not only aware of the classic and linear, but not closed-minded, that they didn't leave it open-ended, that it didn't so result that the potential is taken into eventual account. That as these mathematical methods improve and mathematics is so equipped with the necessary fundamental primary central objects, would allow it to get above and beyond the central limit theorem for a uniformization limit and the regularity in the dispersion of the integers for the regularity of the parts of a continuum, that these kinds of complements that will further advise mathematical foundations and as after logical foundations as for philosophy, the philosophy of science, that thus will so be equipped our models of physics, here as we've been discussing the superfluid, the superclassical, superconductivity, and what reflect these inversions or reciprocals of the fundamental limits and bounds, what are fundamental limits after the restitution and oscillation of the dissipation and attenuation, and how each is primary in its setting, yet together they somehow combine. That thus the dually null and universal are the same thing, and by flipping every single bit in this digital binary universe, there's nothing different than what it is already. That via these kinds of approaches, we can take what we garner from Gödel's incompleteness theorems as not running out the bounds and a sign that says abandon hope, yet instead that it was simply a touchstone of the time saying there still exists that beyond here. And so this kind of rereading leads to derivations again, or a chance to reevaluate the setting and the context in a fuller setting and a context. Thus the results that in accords with what we have as our philosophy of science and as rational agencies each and reasoning beings, that we can get a grip and keep a grip and find these footholds in the edifice of the schools of men, all climbed on the shoulders of giants, that this tower of rain, as it were, finds that we can talk about the objects of mathematics as the same as the objects of logic, as the same as the objects of thought, as the same of a monist's and for some a monotheist's whole universe. Thus that in this way it reflects that the traditions are so relevant and that those touchstones of the early 19th or early 20th century, the early 1900s, and the way things have been formalized and developed since then for all of science and the hard sciences and even the soft sciences to employ, that in this manner we can arrive at why this form of conscientious conscientious science allows us to have really a fresh new look at things, and that is at once formally rigorous for all the manners of the classical and linear and the applied, and then as we see, for example, how it's built out after particle wave duality and these other known limitations of our description and their models, that by so equipping the models with this mathematical background and foundation, we can so equip the models of the physics with this foundation, it will so result a higher state of knowledge. So I've been studying this for some time. Then the other part, or what was discussed, kind of in closing in the last talk, was about these efforts in terms of the pieces of the science, and here I'd really almost rather restrict it to the hard science, because as we get into the realm of feelings, emotions, and beliefs, and what arises in complexity theory as of the soft sciences or the behavioral sciences, that it's really much more for a matter of that the hard sciences are amenable to the scientific method. And so then for questions of faith and belief in the mysterious and miracles and this kind of thing, or for matters of the subjective or the plainly subjective, or that which is as for matters of rhetoric instead of reason, that there is a science of that. There is if there's a true theory, it includes a quite accurate and detailed description of a theory of lies and how to maintain fabrication. But what we're allowed to consider when the milieu includes this perfect theory we attain to is that then we can put down things like the multiple worlds hypothesis, which is unscientific. We can put down some things also like dark matter, which is unscientific. And we can put down some of these other notions which reflect a gap in what is offered. And then as we get to where the real numbers of infinity and infinitesimals for our continuum about our discrete and continuous all come together, that then we can further posit why a reasoning, rational agency can arrive at a mathematical universe hypothesis without much more than someone to talk to about it, and a conscientious approach to science and reasoning and the objects of philosophy. So when we look at something like Herman Weil's book, which we leaf through a bit of the introduction as after it was mentioned by Stephen Pollard and Thomas Boll, the translators, that John Corcoran, a scholar in axiomalist natural deduction, had contributed quite some input and comment on the translation and the intended receipt. That then there's how we look to them these days is that the other key thing, again, at the end of the last talk, was that many of the mathematical models and the numerical methods, as from trigonometry, as from analysis, as from our theories of the expansions of integrals, and the theories of series that establish what are the identities after equalities in our systems of equations as of tautologies, and the duals or the either sides of these things, has that, for example, this book written in the 1970s and this book as published 40 years later, 50 years later, still share many and most of the same formalisms, and they have many or most of the same common and widely instructed parts of our curriculums. And so that looking at these as for a deconstruction of them and the science or their historiography, which is essentially a methodical history, that we arrive at why when we look at these things and from the very fundamental parts, we're able to establish new means of derivation that then that involves a translation to the process of each of these numerical methods and these approaches and these what are taken as the ways and the very important ways that keep these things well behaved and understood and predictable or as of what can be identified and what can be indicated. That it's possible then to consider how to approach that from the side. What results is how then there's a methodical treatment to these methods, which makes it so that after an apologetics for the foundations, an explanation of things, why what we knew was not complete and how when we revisit it, it can be better, that then the approach is also for all the numerical methods and for what are the real fundamental things, And then also about these nonlinear effects, or when we have the phase transition, or as we have about these continuity laws, where we can revisit these when we're able to put down Heisenberg uncertainty, when we're able to revisit Hubble after the redshift differences since 100 years ago, or Higgs, that the Higgs boson has a big divot in the middle, or revisit Heisenberg, Hubble, and Higgs, that these sorts of approaches can lead us to possibilities to make new derivations, not just in the foundations of mathematics, after revisiting Cantor, Gödel, and Russell, but also that for Heisenberg, Hubble, and Higgs, that it's possible to stand up next to them other factors that for Newton, then we have the ideas of Fatio and Lesage, and how we can talk about truly fundamental unifying guiding principles, the first principles and final cause, as was talked about. Thus, the results, the objects of the theory, are more descriptive, and then that we find what is possible to derive and rederive in this wider context, and that it makes for a neater, smaller, more comprehensible setting for the context of all matters of the technical philosophy, logic, mathematics, following that science, and the natural sciences, which is called physics. Right. There are a variety of jokes about professions. So in mathematics and science and computer programming and these kinds of things, it usually involves jokes about, say, a statistician, a logician, a mathematician, and an engineer of some sort, and a computer programmer. And then these, the deeper you go into the field and the more specialized the knowledge, then these are defined in the fields. Like, what do the topologists and the rheologists say to each other? I don't know, but they think it's funny. And so then with regards to that kind of stuff, it was that in a group of travelers of scientific professions of a sort were on a train from England to Scotland. And as they crossed the rolling merry hills of England, there were fields of sheep and flocks all around. And sheep are white or black. And that there are white sheep and there are black sheep. And so as they crested a rise and entered Scotland, they came upon a hill, and standing on this hill was a sheep, and the sheep was black. And so one of the persons said, "Wow, we've entered Scotland, and I'm a statistician, so as far as I can tell from all the samples I have, all the sheep in Scotland are black." And so the statistician was led to, and maybe that's the experimental physicist, or however you sort of care to describe these preconceptions that people have about this thing. And so the second person said something that's like, "Aha, but all we can tell is that in all of Scotland, there is at least one sheep which is black." And this somewhat mollified the participants, and they thought upon this and scratched their beards or their clean-shaven faces of a sort. And then the third person said, "Aha, but you have still left in place your preconceived notion that all we can tell from this entry to Scotland is there is at least one sheep, at least one side of which is black." Because he'd even gone further than that. Everyone knows that the sheep are quite usually of one overall tone. That it's so reflected that his preconceptions were shown as to how then all the other participants had to reevaluate why they had so made it tractable in their working theory to arrive at what they did, that it becomes explicit in that sense. And as regards to then whether the working theories pragmatically need that level of knowledge or need that level of analysis, whether it's right to be a skeptic or a cynic, with regards to whether it's right to be a critic or a promoter of a sort, that these are the kinds of things that when we're making jokes about the profession, and for example, like, there's that mathematician again, every time there's a fire he takes a nap, or that otherwise that they're jokes about professions, that these are innocuous and not expensive people, but meant to make you think. That when something strikes you as funny, it often is, as regards to it activates something in your brain that's the perceptron, that determines something that is an indicator of truth. And that is why in the large that, there are 12 kinds of jokes, and we all knew these in their general forms forever. And they kind of reflect in the perceptions of people and their notions and their preconceived notions and what's overturned when there is something funny, or what's arrived at or confirmed when something's funny. That these are the kinds of things that when you might talk about the science of a joke, that it's not necessarily very funny anymore. So how I want to frame that is that in the nonlinear electromechanical effects and applications, when we're talking about the contrivances and the settings and what we let things to be, how we're able to define that things are determined by their ratios and quantities, that things are determined by their self-parameterizations, things are determined by the implicit, things are determined by these symbolic variables, and they're evaluated according to these regions, these bounds that have well-defined behavior. That basically it involves, in terms of our sheep, is that we have a sheep and we paint one side green and one side red, and what's red and green all over is this sheep we painted. And what we have then with regards to that is we set it up so that these various burdens, donkeys or what, that are so indicated of how the system is contrived in this Rube Goldberger device of a setting and a system of things, is to reduce and actually make for what's contrived are and establish preconceived notions. That thusly, these are the things what follow for our derivation. So going back to the story of how that before has defined how we've made rigor for things, because we're able to keep some things fixed while other things are let free, that we have some things independent while other things on them are so dependent. And that otherwise then we're able to build the model of mathematics as follows: geometry, the most perhaps fundamental form of mathematics. As for what is arithmetic, the theory of numbers, which is the same in a very usual setting. And then as for algebra, which inherently is as of operations over them, in a sense different, although at the same time in its own setting so tractable. That then for functional theory and the objects of numbers, geometry, functions, and the operator calculus, for arithmetic and algebra, and that when we have these in terms of set theory and category theory, as with regards to the arrow function, and how we can make derivations after what's called inference, then we have as for inductive inference and deductive inference, and various forms of deductive inference, if after the one way of inductive inference, as what follows, it's established that inductive inference is in effect courtesy deductive inference. That it so follows that it all gets along. So we had started to read chapter 4 as we got into the variational method. So this would be the same section. After determining for the acoustic wave convolver the amplitude as a function of the initial states and the dimensions of the device, or its volume, and the material properties of the device, and the earlier development of the models of the propagation of the waves, in terms of here the energy or impetus or excitation, the inputs, in terms of time, everything's fundamentally parameterized by time. Then we get to the variational method. So I mentioned a lot about numerical methods, and so here's about the first time it's mentioned in this book. 4.2, variational method. Efficient numerical methods, such as the finite element one, are based on a variational foundation of the problem under consideration. To that purpose, consider the equations of the linear, emphasis authors, theory of piezoelectricity with prescribed volume and surface force densities, F underscore tilde and Q underscore tilde, respectively. Therefore, for frequency omega, these read negative rho sub r omega squared u sub j minus c ijkl uk comma li minus e lij phi comma li equals big F underscore j in little v. That's 4.8. 4.9 reads E sub ikl u sub k comma li minus epsilon il phi comma li equals 0. Continuity law, a statement that it's so arrived at those quantities must establish the additive identity and the multiplicative annihilator in the conditions of arithmetic that the objects of what's usually the field of the numbers has the additive identity and the multiplicative annihilator are both 0. It's in the center. That's 4.9. 4.10 reads quantity ni times the quantity cijkl u comma k comma l plus e sub lij phi sub comma l. This is where a comma is actually in the subscript. So as per the Christoffel tensor and e of lij phi comma l, these described in the preceding chapters, that quantity equals q sub j. So he's thus defined the prescribed volume and surface force densities F and Q, and the index J must equal, according to these, that is basically indicating that there's a torsion in effect, or that it's a uniform or symmetrical as about how the wave propagates, that there's a line through it. And the line crosses 0. 4.11. N sub I, the same quantity as the previous, times E comma IKL, the other indices is reversed, U comma K comma L, minus epsilon sub IL phi sub comma L quantity, and that reflects the same term as was 0 in V, equals omega sub F on delta V. So in V denotes 0, but the delta V is non-zero, and it happens that it's times a constant, which means it's a differential function, and so it would admit a solution as a differential equation. And this is as where the parameterization by the initial values of the wave propagation through this acoustic convolver so set up. Phi equals phi naught on dv phi. So d with the partial respect to phi is that d, again with the partial of v, is that he's got the raw differential there and the raw partial differential there. That saying is it as on is with regards to 4.8 and 4.9 being in v for velocity, and delta v, or the change with respect to such, otherwise raw. And then he goes on to describe what that is, where dv sub phi is that part of dv which is at an imposed electric potential, metallized part of the boundary. Here's describing this contrivance. It is readily checked that equations 4.8 through 4.12 follow from the vanishing first-order variation of the Lagrangian. Star equals complex conjugate. He indicates that in this following note that star for the matrix equals complex conjugate. The Lagrangian is a system parameterized by time. And there's more detail to it than that. It says if after tensorial quantities that after the Hermitian and self-adjoint that the Hamiltonian emits a solution, and the Lagrangian is as of fundamental systems all parameterized by time. The Lagrangian equals 1/2 big quantity, all the rest within, integral of a term in rho sub r, a term in the Christoffel tensor, and a multiple of the first term of the arithmetic identity, as we'll call that multiplicative annihilator additive identity, minus the other half of that, or that essentially it's multiplied the first part of it by 2, and it's a little bit different in the organization, but that otherwise it's in the same terms. That integral over v of that dv minus the integral of dv, and this is a somewhat unusual notation in terms of my familiarity with Leibniz's notation, that the range of integration is given as dv omega sub f phi star dA, so he's integrating over the area dv, and that minus the integral over same dv q sub j, which was defined as the surface force density, where the volume force density and surface force density would be in different units, but they still respect a scalar of a sort in their units. dv of q sub j u sub j star dA, again in the area. That term minus the integral in dv phi or dv phi of phi minus phi naught, or the value given the initial value, its displacement, of the quantity, in brackets, n sub I eijkl u star k comma l, or that component of the constraint of the implicit of the term of the descriptor of the change in the volume and surface force densities, where besides that the density is a scalar at an instant, that in time it still changes, that this other constraint, with though the u term is complex conjugate minus EIL phi, it's termed the complex conjugate, but otherwise as of the same constraint about omega f of the field, minus omega f, so it's able to result that the displacement of the one term times the displacement of the other term, dot dA plus cc, a constant of dot dot dot. I'd imagine that plus c dot c refers to a constant of this variational idea, that where there's always an abstract constant that results after an integration or this sort of thing, and how that goes with regards to the solutions of integrals. The last contribution has been added to account for the condition 4.12 with regards to that phi equals phi naught, CFR Holland and EP Earness, design of resonant piezoelectric devices, research monograph number 56, MIT Press, Cambridge, Massachusetts, 1969. The above variational principle, delta Lagrangian equals 0, can be exploited as follows. The functions u sub j and phi can be decomposed in linear combinations of independent test functions, emphasis the author, selected in such a way, for instance, so that surface integrals vanish identically, i.e. the boundary conditions are automatically satisfied. Here he's further establishing the contrivance, what we compute for these things given the material properties and the material coefficients, and all went in to define what these quantities are, and all went in to define how these identities and these equalities resulting and the approximations so resulting are so defined that the test functions are what, in terms of a linear combination of the independent, are these things that are linear independent in a sense, and establish various results and theorems of vector spaces in linear analysis and linear algebra. That the surface integrals vanish identically, that they're identical is almost as with regards to that relation to the term identity, that they vanish identically so that their boundary conditions automatically satisfied. There's canceling away what's otherwise this extended non-tractable derivation, which cannot be computed. Then for Lagrangian to be stationary, that stationary is, it's usually as with respect to time, but it's as with respect to the solutions of systems of equations, these integral and differential equations, and I need to refresh my knowledge of the exact definition. It is sufficient that all partial derivatives with respect to these functions vanish. Thus, given that the partial derivatives, which are in these orthonormal vector bases pretty much, but as so translated and as so transformed, and as with respect to the tensorial setting, that it's possible to say that there's zero. This yields a linear system of which the unknowns are the coefficients of the linear combinations. So this is a sort of plug-and-pray methodology, but it also then just defines for various implicits that fit that they work out. And this is the essence of Ritz's method, R-A-T-Z, Ritz. In complicated problems, the test functions cannot be obtained easily. Then one can use the finite difference method, in which the volume V is discretized into elementary volumes V sub alpha, in which a simple dependence of the fields U sub j and phi can be assumed in terms of coordinates. This is where the methods of finite differences are great, and they add up to most all the usual things that can be made rational and algebraic. And that here we're dealing with continuous quantities and the linear and nonlinear. That otherwise it's as categorized among numerical methods, which are always having a non-zero error term, or that if it is zero, that it's only coincidence. So then that's reading out the 4.2, the variational method, and this particular variational method in this setting of the acoustic wave convolver, and as that so reflects what would be some kind of device that would so reflect how those could be composed to make an array of these devices, as to how it's possible then so define how that what flows through them would be well defined, and then what regards to their properties as an amplifier or an oscillator or an accumulator and some of these other types of usual simple machines that comprise the larger integrated circuits. That's the thing. So then the next section talks about linear and nonlinear theory, and this reflects back to his organization in earlier chapters of laying out the linear approach and the linear solutions, and then adding on to those a means of lowering the rank and order of the nonlinear contributions, and as what regards to how those pick up. And it looks that it's similar if he has a similar sort of analysis and derivation, though it gets quite a bit more complicated in the proceeding of what follows in various introduced terms in chapter 4 of the nonlinear section, and that is about the most involved tract thus far in this book that, yes, is yet to be read. And so just skipping forward a bit more, that's more than less what would be the end of the book, and as to where he arrives at this acoustic wave convolver, and then he describes what that means in terms of without this mathematics, there is not a way to do this, whereas with these, that it fundamentally provides a rational basis to explain how and why it is so. So it remains to be picked up then the following section after chapter 4's last section, 4.3, that before 4.4 with numerical results that so describe the results. That linear and nonlinear theory begins the cross-section of the waveguide convolver in the interaction zone, looks like in figure 4.4. The superimposed electrode is a conductor, e.g. aluminium, where aluminium is a European name for aluminum, while the substrate is a piezoelectric crystal, e.g. lithium niobate, and lithium niobium with 3 oxygen. The above recalled variational principle must be applied to the whole system depicted in figure 4.4. The variational principle must be applied to the whole system, where it is indicating that in parts it wouldn't be in effect or something like that. So that's something to pick up and read on later, if there's just to be kind of a reading and interface of this these formulas to terms. Then we can talk about constants of elasticity, electroelasticity, dielectricity, and electrostriction. And with regards to Lagrangian of a forced continuum of the excitations, that the Lagrangian is written of the conductor with regards to its circuits, and when it's short-circuited, that the figure of merit is defined to result some descriptive terms in constants and coefficients, that the figure of merit is given in terms of root mean squared and various terms that result a formula in 3 variables. The quantities z naught and m are measurable characteristic quantities. Here they are computed. And so he's just describing that in the empirical, of course, we would just measure things to measure twice, cut once. Vis-a-vis in the theoretical here, we hope to employ these methods to arrive that before we measure and cut, we kind of already know what the answer is. So that's kind of the reading for today, and we've reached a point in Maugin's work where it's over the course of 10 or 15 hours, and this is most of the time that I spent reading this book, although I've looked at it many, many times over the past several months in trying to understand how to approach its contents. That then, following that there is basically a studious reading of the book and its matters and materials, it's possible to take away, then reading more and more of these books, how it gets possible to find out what they have in common, their commonalities, and what makes each of them unique. And then with regards to when we learn how things may or may not be so, and as we've been talking about the fields of linear analysis, about topology, about the arithmetic and the algebra, and how they're so closely related, yet how they're duals and how they're at odds with each other, about the additive and multiplicative in the arithmetic, and how in the one sense they're totally defined and closed in terms of each other, yet that in some degenerate systems of arithmetic it may not be so. Or that one or the other of the additive identity and the multiplicative annihilator have its place. Or that vis-a-vis how things are restricted to the range of the unit or the full unit, how those things are in place. Then there's the talk about, as we've been talking about, why the continuum is so important, and why then of this simple equations as of equalities, as of inequalities, as of what enables the free application of algebra, as of the closure of arithmetic, and the free operation of arithmetic with regards to the closures of algebra. It leads us back to how early in the development there were these tensorial quantities and the introduction of their formalisms, and as of after how their product spaces are so defined, and then what it entails to pick up a development like the Christoffel acoustic tensor with regards to crystallography and Schläfli and these classes of materials, and then with regards to all the descriptive terms that reflect all these different aspects of the fields. These fields, as when they are superimposed together, result a unified field. That these are the kinds of things that go into a reasonably complex mathematical development. Here with the goal of a kind of thing is reducing that for a given particular configuration to a formula with 3 variables. Real numbers. So that's the kind of thing that gets into it, where if we were to look at something like differential geometry, curved surfaces and manifolds, or differential equations, their solutions using symmetries, deconstructive criticism, I mean, this is basically relevant, though this is more for the literary criticism and kind of our soft science. In constructing a view of the world and of existence, onto-theological man can assume a stance of disinterest and impersonality. He can distinguish through observation the permanent from the changing. He can withhold his care and interest. Thus man is able to place before or to present to himself in presence and uncertainty objects for analysis, manipulation, and calculation. He can exercise will and power over the world. In all of this, metaphysical man expresses a profoundly spatial view of existence. Well, then the author here goes on to describe that Spanos aims to destroy this, in quotes, the traditional spatial model or worldview in favor of a temporal systematics. What does such destruction entail? This is in the chapter called The Truth of Literature. And I recently read another book called The Truth of Literature and Poetry, and he gave it to some friends. By destruction, I do not, of course, mean annihilation. I mean rather a hermeneutic project grounded in an understanding of truth as aletheia. And here we can refer to the dia-a-letheism of what's called Grand Priest's efforts in what's called paraconsistency, or how to resolve the paradoxes of logic because it's regular in dispersion and regular in attenuation. That the aletheia is where lethe is the dream, and so this is the reality, bringing into the open from hiddenness or oblivion, and assuming the form of a destruction, a disassembling of a spatial figure, such as that which Heidegger undertakes in his dialogue with ... the systematic philosophy of what he has called the Western onto-theological tradition. Heidegger. In a Heideggerian manner, Spanos conceives destruction as an interpretive enterprise oriented towards overturning the systematic philosophy of tradition, especially spatial paradigm, in order to reveal hidden and forgotten possibilities through careful destructuring of the now dominant metaphysical formations of truth. So here, this gets into why in the technically philosophical that what is in terms of deconstructive criticism, and so that we can kind of leave behind postmodernism and some of these efforts of the ethereal and the dreaming of these things, or the interpretation of things in a phenomenology that isn't so necessarily objective, or that I'm somewhat skewed or biased in terms of that. I feel that deconstruction has got a bad name because it's misused in the critical theory that's not very critical and not very theory. So in destructive inquiry, that's where we get to a reconstruction, because it's here where I would frame in parallel with the what's called renormalization of quantum physics, which we discussed last time. Richard Feynman's and others' efforts in the description of quantum mechanics, like quantum chromodynamics and quantum electrodynamics and quantum dynamics in particular, are all about what happens when we take something that's a continuum and make it as a point, or when we have something as a point and rationalize it as a continuum. So that is the effort of the renormalization. It's about the quantum and the continuous and the quantum and the discrete. So then what that follows, though, is a denormalization of sorts. Already our model had built into it that our theoretical model of the point particle made for in this quantum analysis, and giving it certain properties as about the propagation of superimposed fields in a wave theory. That this book in literary deconstructionism is really quite good and very much quite technical. That I'm glad I have this, and we'll talk a little bit more about how the author Vincent B. Leach, Leitch, in an advanced introduction to deconstructive criticism, details that, as the back cover reads, what is deconstructive theory? Why is everyone talking about text and interpretation in a new way? Why do the explanations of the famous forerunners of the movement, as well as their followers, seem obscure, if not hopelessly opaque? In Deconstructive Criticism, an advanced introduction, Vincent B. Leach provides the as yet uninitiated reader with a lucid and comprehensive understanding of established thought and the work currently being done in the field. Leach addresses the questions posed by the major figures Saussure, Lacan, Lévi-Strauss, Heidegger, Derrida, Barthes, and Foucault, although I'm not quite sure which Foucault he's talking about, then penetrates and displays the subtle intricacies of their answers. Concise, in-depth analyses, surveys of historical background, and helpful overviews make deconstructive criticism the ideal prelude to the study of deconstructive theory. Deconstructive criticism neither vulgarizes and oversimplifies deconstruction nor protects it for an elite, and this is indeed a substantial achievement. Leach does not fear the mysteries of deconstruction, but provides in his sprightly, fair-minded, and comprehensive book an advanced primer for non-initiates. And the cover illustration is Diego Velázquez's Las Meninas, used by permission of the Prado, Madrid, Spain, from Columbia University Press, New York, printed in the USA. So there's that. That's pretty great. I was quite impressed with it. This is Meaning, Truth, and God is a series and collection of essays as from Boston University and Notre Dame University about meaning, truth, and God, and interpretations as of about the 1980s, and irrationalization. A History of the Circle, Mathematical Reasoning and the Physical Universe is a book by Ernest Zebrowski Jr., printed by Rutgers University Press, New Brunswick, New Jersey. Its first paperback printing was 2000. It's copyright 1999. As we've been talking about periodic motion and 2 pi radians, and which is a dimensionless quantity, the radian, but yet it still reflects a setting. It's just got a 0 dimension. That 2 pi and the ratio of the radius to the circumference, or diameter to the circumference if you so care. And these type of things are very, very, of course, fundamental and related to the quadrature and the quadratic sieve, and thus relating the quadrature to the quadratic sieve to the prime number distribution, and relating the quadratic to the circular. That he has a chapter on oscillations and a chapter on waves. And then when we talk about the waves, then we also can talk about the orbits of things, that they're kind of the same thing if you look at them in parallel and as from opposite ends. That will also result that this is a very, very interesting work about the centripetal and centrifugal. And what I would read of it is, of course, for a theory that unifies gravity with quantum mechanics and general relativity, with gravity in the middle, making a fall gravity, as to why then such notions as a unified field theory so fall together. That's pretty cool. I'll look at that some more later. That then otherwise here, let's see, some minutes into it. So there's that. Then we've looked at most of these other works at least a bit here. Here's Leonardo on painting. This is the Mona Lisa from Leonardo da Vinci from Paris, the Musée du Louvre. And this anthology of writings by Leonardo da Vinci, with a selection of documents relating to his career as an artist, is edited by Martin Camp and selected and translated by Martin Camp and Margaret Walker. Leonardo's writings on painting, among the most remarkable from any era, were never edited by Leonardo himself into a coherent treatise. The book, known as Leonardo's Treatise on Painting, first published in 1651, comprises a compilation of quotations described by one early translator as a chaos of intelligence. This anthology aims to bring order onto the chaos, so Leonardo's views can be read in a logical and sequential manner. The authors have edited material not only from the treatise, but also from Leonardo's surviving manuscripts and from other primary sources, some of which are here translated for the first time. Included among these are Leonardo's own letters and memoranda, letters by contemporaries, and important documents to which he was a signatory. The book begins by looking at Leonardo's general principles of painting, including the famous Paragone, the comparison of the arts. Then follow sections on the optical foundations of art, the human body, the appearance of nature, and the practice of painting, including instructions for the artist and evocative accounts of subject matter. The translation remains close to the originals, with particular attention paid to technical terms that have changed in meaning since the time of writing. Illustrations from Leonardo's paintings and drawings are interwoven with the text to show the relationship between theory and practice. This book, the authoritative anthology of Leonardo's writings on painting, is an invaluable reference work for art historians as well as for anyone interested in the mind and methods of one of the world's greatest creative geniuses. Yeah, Leonardo's pretty great. Oh, that's wonderful. Virgin and Child with a Yarn Winder, collection of Buccleuch and Queensberry. As if desirous of the cross, he smiles and holds it firm and is unwilling to yield it to his mother, who seems to want to take it away from him. Oh, that's beautiful. Virgin, Child, and St. Anne. His mother, half rising from the lap of St. Anne, takes hold of the child to separate him from the lamb, a sacrificial animal signifying the passion. Well, these are some of the things here. And here's a scythed chariot and armored cars, London, British Museum. I will make covered vehicles safe and unassailable, which will penetrate the enemy and their artillery. In short, as the variety of circumstances dictate, I will make an infinite number of items for attack and defense. Leonardo da Vinci. Well, this is for matters of perspective, matters of form, and how basically what we draw and paint is kind of the opposite of how light brings it to our eyes. We follow matters of perspective as our perspective. We draw shadows, not light them. Though, of course, there's both kinds of color models. There's the additive and the subtractive. There are colors that add together to make colors, and there's colors that subtract from each other to make colors. It's called the color wheels. And so then when we talk about models of vision, we have what's called luminance, and then redshift chrominance and blue shift chrominance. And so the luminous part is like the grayscale image, black and white, and it's shades of green, as it were. And then the luminance has then, that being the intensity of light, that there's the chrominance and the chrominance, where the chrominance, either way of the redshift and blue shift, allows, that's what's called a tri-stimulus color space. And in this tri-stimulus color space, then various colors in this range of frequencies is according to the frequency of light, and the reflective light according to albedo, and emitted light with regards to the candle, that in what's called the tri-stimulus color space, that most of the colors can be represented. Now, the YCBCR, which is the color of JPEG images, for example, that's its color space, has then that so follows, for example, something like red, green, blue. When we're familiar with red, green, blue as the tri-stimulus color space in those primary additive colors that results, according to the pointillism, what results the old-fashioned television picture tube, as with regards to red, green, and blue, and when we talked about the color space in those colors. Then the other, some other tri-stimulus color spaces that are of interest are basically that the Comité d'éclairage back in Paris in the 1920s invented what's called XYZ color space and ABC color space. And those reflect the additive colors as according to pigments, and what result that these are, when you get something like the Pantone colors or colors of printing and this kind of thing, vis-a-vis the colors that are emitted by the stimulation of light, that they are fundamentally different in their operation. There is yet that the tri-stimulus color space, or three different components and coordinates, result making the color wheel of, in terms of that our color wheels have, that then the palette that you usually pick from, for example, in selecting a color from a graphical user interface on a computer, is something along the lines of one of these color spaces. And other ones include hue, saturation, and intensity, or hue, saturation, and brightness. That these are two, again, more kinds of color spaces. So that as we begin to talk about things like red, green, blue, ABC, and XYZ, YCBCR, that's luminance is Y, and chrominance blue and chrominance red. And then there's HSV and HSI, and then we have these higher fidelity color ranges where the multispectral analysis of the frequencies of reflections and emission of light is about the spectrum. And we're familiar with mostly with the spectrum, with splitting it with the prism and resulting what's called the rainbow. And there's a great book about the rainbow by Carl Boyer, who also wrote the great book on the calculus. That the perception of form and as of geometry and perspective is one thing, and then the idea of painting is another thing. I guess if there's one lesson I recalled learning as a child was that my ability to reproduce drawings of realistic scenes was rather poor. And it's really a matter of practice. At some point in time, I could draw a horse or a reasonable simulacrum, a facsimile of something from a comic book, like a person. But that then, with regards to the reconstruction of realistic images, one thing we learned in our exposures to the enrichments of art education and art curriculum was the drawing upside down. So what you do is you get a picture you're supposed to reproduce as by drawing, and instead of using something like a pantograph arm or tracing it or this and that kind of thing, you turn it upside down. And then what you do is you draw what you see upside down. And what happens in the brain between where you image it in your eyes, in your mind, and reproduce that on the paper as in the translation, is that instead of the step that automatically in your brain has introduced this preconceived notion of what it is, and that the drawing is, for example, stymied, that one balks drawing something because like I cannot reproduce this image from my scrawl as what I see in all its richness and all its context in my mind. That by turning the picture upside down and drawing the upside picture, it basically distinguishes that the brain then results that when you draw, it's a simple matter of telemetry, and that in this manner it's possible to more easily recreate close to realistic renditions of proportion matching, or the realistic in these things. And then there's basically that impressionism is the people with very bad nearsightedness, and that's really what they see. It's realism. And then I guess if there's one thing is that Leonardo is an interesting character or whatever, and he invented a writing where he would just write things backward, entirely backward. And so then when he put his script and writings up to a mirror, it was in the correct orientation, left to right. And so when we talk about orientation, right to left and left to right, and the symmetry and chirality, which way does the world spin and why, then that's for the theory of mirrors, what is up and down versus left and right, stereoscopic vision, theory of colors. And in our eyes we have rods and cones, and we also have various interesting pigments and related complexes that make vision possible. And the largest nerve in the body is the optical nerve, and it connects the eye to the forebrain. Then these notions of art are as well technical and parts of our phenomenology and semiotics, where when we're talking about the senses, five physical senses, taste, touch, hearing, sight, and smell, that then we also have our word sense and our object sense and our number sense, and what results then in the very abstract that this object sense is as of our rational agency vis-a-vis the stimulus and response, or what is sense and what is semiotics and what is phenomenology and what is the perceptron. Well then, hey, have a great day. We've looked through most of these books now at least a little bit, and we're almost done with nonlinear electromechanical effects and applications. So here's some more of this. That's that. I have some more books, and we'll be getting to them some other time. So long.